Hello everyone, my name is Nikolentzos, and in this video I will present our work entitled Geometric Random Walk Graph Neural Networks via Implicit Layers. This is joint work with Professor Michalis Vazirgiannis. In the past years, graph structure data has experienced an enormous growth, mainly because graphs arise in several different domains. For instance, in chemistry, molecules can be represented as graphs. In medicine, different types of networks arise, such as brain networks, and social networks, for instance, are typically mapped to graph structures where nodes represent users and edges capture friendship relationships. Several different problems can be defined on graphs. For instance, some problems might focus on nodes, others on edges and subgraphs. In this work, we're interested in problems where each sample is an entire graph, and examples of such problems include graph classification and graph regression. These problems, they have attracted a lot of attention recently, mainly because they lie at the core of important real-world applications. I will briefly mention two of them: predicting the quantum mechanical properties of molecules and modeling physical systems. Graph neural networks have been the prominent approach for dealing with such problems in recent years. And most of these models, they belong to the family of message passing neural networks. These models, they have achieved great success in several applications. However, their design is a bit counterintuitive. One would expect the hidden layers of those models to consist of trainable graphs. Instead, they consist of fully connected layers followed by some aggregation function. In our previous work, we proposed a more intuitive model, so-called random walk graph neural network, which uses the p-step random walk kernel to compare an input graph against some trainable graphs. However, this model focuses on local neighborhoods of nodes, and it might fail to capture the overall shape of graphs and also potential interactions between nodes that are far from each other in the network. In this work, we propose a new model which counts common walks of up to infinite length and can thus capture the overall structure of graphs. Now some preliminaries. Given two graphs G1 and G2, their product graph is a new graph whose node set is equal to the Cartesian product of the node sets of the two graphs. And two nodes in the product graph are connected by an edge if the two pairs of nodes from which the two nodes emerged are connected by an edge in G1 and G2. And one nice property of the product graph is that if we perform a walk on this graph, it is equivalent to performing a simultaneous walk on G1 and G2. It is also well known that if we raise the adjacency matrix of a graph into some power, P, then the element in position I, j of the emerging matrix gives us the number of walks of length P from node I to node J. And if we raise the adjacency matrix of the product graph to some power P, then we essentially count the number of common walks of length P in the two graphs. And this is the main idea behind the random walk kernel. And the geometric variant of this kernel counts common walks of up to infinite length in two graphs. You can see the formula of the kernel on the bottom of the slide, and it is well known that this geometric series will converge if the value of hyperparameter lambda satisfies some constraint. And also the kernel can be computed in closed form. Let's now move on to the proposed geometric random walk graph neural network model. The model contains a set of trainable hidden graphs, and each one of these graphs is an undirected graph without self-loops. And if n denotes the number of nodes of each trainable hidden graph, Then we use n times n minus 1 over 2 trainable parameters to represent its graph. And we apply the ReLU function pointwise to those parameters to make sure that we obtain a valid adjacency matrix for these graphs. Then the model computes, given some input graph G, computes the kernel between the input graph and its trainable hidden graph. The output of the kernel is a scalar, and we stack all these scalars into a vector HG, which we can think of as the vector representation of the input graph G. And the proposed geometric random walk graph neural network generalizes the random walk graph neural network such that it can count walks of up to infinite length. This is an illustration of the proposed model. This is the input graph G. This is the set of trainable hidden graphs. Each hidden graph is compared against the input graph using the geometric random walk kernel, and we end up with a four-dimensional vector, which is passed on to further fully connected layers to compute the output. If G1 and G2 contain n nodes, then the dimension of the product, the adjacency matrix of the product graph is equal to n squared times n squared. And inverting such a matrix of this dimension using standard Gauss-Jordan elimination requires n to the power of 6 time, which is prohibitive for real-world applications. So we need to use some alternative technique to compute the kernel, and we follow some previous approach. And instead of inverting this matrix, we solve a linear system, the one you can see here for Z. And once we have computed Z, we can just sum up its elements, and this gives us the kernel value. To solve this linear system, we use fixed point methods. So we can rewrite the system as you can see on the slide, and then we can iteratively compute the value of Z till it's very close to its previous value, or a specific number of iterations has been reached. But still, solving this system requires explicitly constructing the adjacency matrix of the product graph, which is pretty expensive. So we need to make the model more efficient, and we capitalize on well-known properties from linear algebra. And instead of computing this product between the adjacency matrix of the product graph and Z, we instead compute a matrix product between those three matrices, and the complexity now is n squared times C, where C is the number of nodes of the hidden graph. And instead of solving the system of the previous slide, we solve the system you can see on the bottom of the slide, which is more efficient. Another problem of the proposed model is that to train the model, we need to backpropagate the error through the fixed point solver, and that this requires storing all the intermediate terms, which is expensive. But following recent advances in implicit layers, we propose a more efficient approach where the model needs to have no knowledge of the fixed point solver, and backpropagation can be performed in an efficient manner, which requires constant memory. The model was evaluated on standard real-world graph classification data sets. We followed the experimental setup of a framework for fair comparison of GNNs, and also on 2 graph property prediction datasets from the Open Graph benchmark. This is the first set of results. We report the average accuracy across the 10 folds along with the standard deviation, and the GRWNN is the proposed model, and GRWNN fixed is a variant of the proposed model where we keep the parameters of the trainable graphs fixed. And you can see that on this, the proposed model outperforms the baselines on 2 out of the 5 datasets, while it outperforms the GRWN fixed variant on all 5 datasets. In the case of the social interaction datasets, we once again we can see that the proposed model achieves high levels of performance, and it's the best performing method on 2 out of the 5 datasets. And on these are the results on the 2 OGB datasets. On OGB mole HIV, the model achieves high levels of performance. Its ROC AUC score is close to that of the best performing models, while on OGB code 2, the model does not yield that good performance. It only outperforms the GIN model, and it is even outperformed by GCN. Here you can see on the top the average number of iterations of the fixed point algorithm for different values of lambda on the enzymes dataset. And we can see that for large values of lambda, for instance, equal to 1/5, the geometric series does not converge, and we need 100 about 100 iterations, which is the limit we have set. While for smaller values of lambda, we can see that the algorithm needs only a few number of iterations, so the model is efficient. Its running time is comparable to that of message passing models. And on the bottom, we can see the performance of the model on enzymes as a function of lambda. For large values of lambda equal, for instance, lambda equal to 1/5, we can see that the model achieves a very low accuracies, while performance increases a lot if we decrease the value of lambda. The model achieves about 100% accuracy on the training set and around a bit less than 80% on the validation set. To conclude, in this work, we generalized the random walk graph neural network model such that it can count common walks of up to infinite length. It can capture the global properties of graphs, and it can also capture interactions and dependencies between nodes that are far from each other in the graph. And in our experiments, we found that the model is competitive with other GNN models in different learning tasks.